Back in the 1970s, astronomers made a startling discovery. Our Milky Way galaxy was on the move. We were being pulled by immense, invisible forces toward something we couldn't see. Our destination was hidden behind what's called the Zone of Avoidance, an area of the sky blocked by the gas and dust of our own galaxy's disk. Imagine a small boat drifting on a vast, dark ocean, caught in a current heading toward an unknown place. We weren't alone in this journey. All our neighboring galaxies were moving too. Two astronomers, R. Brent Tully and J. Richard Fisher, used a radio telescope in Australia to study distant galaxies, trying to piece together their movements from limited data. Around the same time, other teams were observing the cosmic microwave background, the faint glow left over from the Big Bang. Both groups independently found the first clues of this grand cosmic flow. The galaxies Tully and Fisher mapped seemed to be heading toward a common point. Meanwhile, the cosmic microwave background showed a slight temperature difference across the sky, a bit warmer in one direction, cooler in the opposite direction. Much of this could be explained by our sun's motion around the galaxy's center. But even after accounting for that, a mystery remained. Something was pulling us, and many other galaxies, at hundreds of kilometers per second toward a specific spot in the universe, as if connected by invisible chains stretching millions of light years. For decades, we couldn't see it or map it. The best we could do was give it a name, the Great Attractor. It was a powerful source of gravity, a single point pulling our entire galaxy and thousands of others, home to countless stars and planets, toward it like moths to a flame. This might seem strange, but it's actually quite normal for our universe. Nothing in the cosmos is truly still. Everything is in motion, from Earth orbiting the Sun, to the Sun moving within our galaxy, to the Milky Way rushing toward the Great Attractor. And that attraction is just the beginning of a much larger story. On September 23, 1999, NASA lost contact with the Mars Climate Orbiter as it approached the red planet. The mission failed completely. The cause was a simple error converting between metric and imperial units. Our universe is defined by motion, and the history of science is, in many ways, the story of our growing understanding of this cosmic restlessness. For thousands of years, brilliant minds in Europe and the Middle East believed Earth stood perfectly still, with the heavens revolving around it. These early astronomers worked hard to predict the motions of the sun, moon, planets, and stars. Their system worked reasonably well, but it was a complicated mathematical mess, relying on circles within circles. Then, in 1543, on his deathbed, Polish astronomer Nicolaus Copernicus published a radical new idea. He placed the sun at the center, motionless, with Earth and the other planets moving around it. Reactions were mixed. It was a bold new vision, but it was also messy and raised difficult questions. Most pressing: if Earth is moving, how can we tell? We know we're moving on Earth's surface because we feel the wind or see landmarks approach. So why don't we feel a great wind from Earth's orbit? Why aren't we flung into space by our planet's rotation? It took centuries and Newton's theory of gravity to get answers. We don't feel Earth's motion because we're moving with it. Space is a vacuum, so there's nothing to push against that would reveal our movement. But how can we be sure Earth is moving? Is there a universal standard? Newton assumed such a fixed reference frame existed. Einstein, however, rejected this idea with his theory of relativity. He stated that all motion is relative. You can only measure your movement compared to something else. From this simple idea flows the rest of relativity. Spacetime, the equivalence of mass and energy, the speed of light limit. Picture two unpowered rocket ships drifting. As you pass each other, you could say you're moving and they're still. But from their perspective, they are moving and you are still. Both views are equally valid. We know Earth spins because of the Coriolis force, which twists air to form hurricanes. Even with no stars in the sky, we could deduce Earth's rotation. But measuring Earth's motion through the wider universe is different. We need another frame of reference, a yardstick. Otherwise, we could rightly claim we are motionless and everything else moves around us. Fortunately, the universe provides the perfect tool. We don't live in a static universe. We live in an expanding one. The cosmos grows larger every day. This expansion gives us a preferred frame of reference, one that expands with the universe. On large scales, galaxies are, on average, moving apart. Any motion on top of this general expansion is special. Cosmologists call this peculiar velocity, and these speeds can be hundreds or thousands of kilometers per second. With this understanding, scientists can trace not just Earth's spin or orbit, but our solar system's path through the galaxy and the Milky Way's journey through the cosmos. Without feeling it, without taking a step, you travel an incredible distance in your lifetime. First, Earth's rotation. Depending on your location, you could be spinning at up to 1,600 kilometers per hour. If you're at the North or South Pole, your speed is 0. Most people live at mid-latitudes, moving at about 1,000 kilometers per hour. Over an 80-year life, that's roughly 1 billion kilometers traveled just from Earth's spin. Then there's Earth's orbit around the Sun, averaging 30 kilometers per second. Over a lifetime, that adds about 80 billion kilometers, though most of this is in a circle, so you're not really going anywhere new. But our motion doesn't stop there. The Sun, along with the entire solar system, orbits the center of the Milky Way. One full revolution takes 230 million years. The Sun's average speed in this orbit is about 230 kilometers per second. Interestingly, this speed is key evidence for dark matter. When we add up all the visible mass within the Sun's orbit, even accounting for unseen stars and gas, there isn't nearly enough to keep the Sun in a stable orbit. Without extra mass, the Sun would have been flung from the galaxy billions of years ago. Yet here it is, held in place by the gravity of invisible dark matter. The Sun also bobs up and down through the galactic plane, like a buoy in an ocean, influenced by gravitational tugs from neighboring stars. Over millions of years, it rises thousands of light years above the plane before plunging back down. Right now, our solar system is passing through a region called the local bubble, a low-density cavity blown out by an ancient supernova. We entered this bubble 5 to 10 million years ago and will traverse its 1,000 light-year expanse for millions more. But that's still not the end. Against the backdrop of universal expansion, our galaxy is on the move, heading straight for our nearest neighbor. Billions of years from now, our night sky will be utterly changed. The moon will be smaller and more distant. The Sun will be larger and brighter. Familiar constellations will be gone, replaced by new stars. And one object will dominate the heavens: the Andromeda Galaxy. Today, Andromeda appears about the size of a fist held at arm's length. In 2.5 billion years, it will fill much of the sky. It won't look like it does now. Its shape will be grossly distorted by immense gravitational forces as it begins to merge with the Milky Way. A billion years later, the sky-filling Andromeda will blaze with giant stars as the collision triggers furious new star formation. Billions of years after that, long after our sun has died, the merger will be complete. The core of the new galaxy will glow brightly. Giant stars will die in supernova flashes. If Earth survives, huddled near the sun's white dwarf remnant, our sky will slowly fade to red, then to black. In the 1920s, Edwin Hubble discovered that the Andromeda Nebula was actually another galaxy, an island universe over 2 million light-years away. Measuring its speed was tricky. Andromeda is so large that early telescope observations of small sections gave wildly different velocities. It wasn't until 1957 that Dutch astronomer Hendrik C. van der Hulst got a reliable measurement. He studied radiation from neutral hydrogen gas. By measuring shifts in this radiation, he found Andromeda moving toward us at an average speed of 296 kilometers per second. This measurement included the sun's motion around the galactic center. Subtracting that gives the true galactic motion, about 100 kilometers per second, in the frame of reference that respects the universe's expansion. Both galaxies are moving toward a common gravitational center, but motion toward us didn't guarantee a collision. Astronomers usually only measure radial motion, toward or away from us. Sideways motion is harder to detect. In 2012, a team led by Sangmo Tony Sohn used the Hubble Space Telescope to measure the motion of thousands of stars within Andromeda. This gave the first clear three-dimensional picture, confirming we are on a collision course. The fun begins in about 2 billion years. As the galaxies approach, their immense gravity will distort their shapes. The physics is similar to ocean tides on Earth. The sides of each galaxy closest to the other feel a stronger pull than the far sides, creating tidal forces that stretch the galaxies. Spiral arms can detach, forming long tidal tails of intense star formation. Bridges of gas and stars can form between them. The actual merger in roughly 5 billion years won't be like a sudden crash. Galaxies are mostly empty space. While the gas tangles and forms shock waves, stars will pass by each other like two swarms of bees. But stars won't escape unharmed. Their orbits will be disrupted, creating chaos. Most stars will survive, but some will be scattered by gravitational encounters, flung out of the galaxy forever. The first close pass will take over 100 million years and will repeat several times over hundreds of millions of years. Each interaction will compress gas, triggering fresh rounds of star formation. At its peak, star formation could be 1,000 times faster than today. For a brief, beautiful moment, the merged galaxy will blaze with millions of new, bright blue stars. But galaxies have a limited gas supply. A quiet galaxy like the Milky Way can use its gas slowly over 100 billion years. A collision burns through it too quickly. Once the new stars die, little gas will remain. The merged galaxy, sometimes called Milkomeda, will become a giant, red, elliptical galaxy, largely incapable of making new stars, doomed to slowly fade as its stars die one by one. This is our best prediction. though some recent simulations suggest the merger might not happen for 8 billion years. We can't watch mergers in real time. They take hundreds of millions of years. Instead, we see snapshots. The merger ignited such intense star formation that the galaxy shines 100 times brighter than the Milky Way. Star formation has already stopped. We see the afterglow. Across the universe, we see countless galaxies merging in various stages. Some collide head-on, others glance off. Some are perpendicular, others slam spiral arms together. Sometimes more than two galaxies grapple for dominance. Galaxy mergers began billions of years ago and will continue into the future. The Milky Way's journey doesn't end with Andromeda. Our motion through the universe continues toward a destination we barely understand. Mathematics can be a crystal ball, letting us peer across space and time. This story begins far from modern cosmology. In 1792, French mathematician Gaspard Monge, as Minister of the Marine, worked on optimizing the transport of goods. Decades later, André-Marie Ampère expanded Monge's work into equations used in economics, like moving resources between mines and factories. During World War II, Soviet mathematician Leonid Kantorovich applied these equations to logistical problems. Then, in the 1970s, Canadian-American cosmologist Jim Peebles realized the same math could describe the efficient movement of mass in galaxy formation. Jim Peebles, from a humble background, studied at Princeton and became a giant in cosmology, a field many considered a dead end in the 1960s. He pioneered modern cosmology, from the growth of cosmic structures to the Big Bang's earliest moments, earning a Nobel Prize in 2019. Later, astronomers Roya Mohey and Andrei Sobolovsky used Peebles' work to turn these equations into a cosmological crystal ball. They found they could take galaxies' current positions and some velocity data to transport them back in time. Since we know how gravity works, we can calculate where galaxies should have been in the past. It's not perfect. Uncertainties grow with each step back, but it works. Using this method, Brent Tully and colleagues created the Cosmic Flows catalogs, mapping tens of thousands of galaxies and reconstructing their motions through time, both past and future. This lets them predict where the Milky Way is headed. Through careful observation and this mathematical crystal ball, we can finally understand the Great Attractor and our ultimate cosmic fate. The universe's expansion gives us a preferred frame of reference to judge motion. We can make detailed velocity maps of nearby galaxies, but it's a difficult task. Thankfully, the universe gives us a snapshot of this reference frame, the cosmic microwave background. The CMB was created when the universe was about 380,000 years old, as it transitioned from a hot plasma to a neutral gas, releasing radiation. This light has two key properties. First, it's everywhere. Every cubic centimeter of space participated in its creation. Second, it's almost perfectly uniform, with temperature variations of only about 1 part in a million. This makes it a perfect snapshot of the cosmological reference frame. Any motion relative to this frame distorts our view of the CMB. It appears blue-shifted, hotter, in our direction of travel and red-shifted, cooler, opposite our direction. This is exactly what we see. The CMB is about 0.0035 Kelvin hotter in the direction of the constellation Leo and cooler by the same amount in Aquarius. This temperature difference, called a dipole, is explained by our motion relative to the CMB frame at about 600 kilometers per second. Part of this speed is from the Sun's orbit and our path toward Andromeda, but after subtracting that, a residue of about 300 kilometers per second remains. The direction of this motion points straight toward the Great Attractor. The grand structures of our universe were built by billions of years of motion. The Milky Way started as a small group of stars and grew through mergers. This story has played out trillions of times across the cosmos in a process called hierarchical structure formation. The universe builds itself like a Lego masterpiece, brick by brick. Structures exist in a hierarchy: galaxies, groups, clusters, and superclusters. Galaxies are already assembled from past mergers. Groups, like our local group containing the Milky Way, Andromeda, Triangulum, and many dwarf galaxies, are still collapsing and merging. About 100 billion years after the Milky Way-Andromeda merger, the rest of the local group will join, forming one megagalaxy. Groups like ours are also moving toward local centers of gravity, galaxy clusters. Our nearest cluster is the Virgo cluster, home to thousands of galaxies, pulling in tens of thousands more. Along with moving toward Andromeda, our local group is falling toward Virgo. This process began shortly after the Big Bang, but only intensified a few billion years ago. As clusters like Virgo grew, their gravity increased, pulling in more material. Long ago, the young Virgo cluster began weakly tugging on the local group. That gentle tug has become a mighty force. Gravity's work doesn't stop at clusters. Clusters are the largest gravitationally bound structures, already complete but always hungry for more. Clusters themselves participate in building the next level, superclusters. Supercluster has always been a loose term for large, coherent structures bigger than clusters. As far back as 1863, astronomers William and John Herschel noted an excess of nebulae toward the Virgo cluster. In the 1950s, astronomer Gerard de Vaucouleurs identified this as a structure, calling it the local supergalaxy, later the local supercluster. But superclusters aren't fully assembled, so they have no clear boundaries. Initially, astronomers thought the Virgo cluster was at the heart of the local supercluster, a collection of about 100 galaxy groups spanning over 100 million light-years. Starting in 2014, Brent Tully and collaborators proposed a new definition based not on size, but on motion. Using the mathematical reconstruction technique, they brought galaxy surveys to life, tracing where tens of thousands of galaxies came from and where they're going. Their motions revealed our local supercluster's true extent. The Milky Way belongs to the local group because we're all moving toward a common center, which will become one giant galaxy. The local group belongs to the Virgo branch of our supercluster because we're all headed toward the Virgo cluster. The Virgo supercluster branch belongs to Laniakea because we're all moving toward Laniakea's center, 100,000 galaxies, spanning over 500 million light-years across 4 branches, all head for a single destination. The beating heart of Laniakea, the local center of attraction for this part of the universe, the final assembly point of a construction project billions of years in the making, the center of it all. The Great Attractor. Our view of the Great Attractor is fuzzy because it lies in the zone of avoidance, obscured by our galaxy's dust. But some light, like radio, infrared, and X-rays, can pierce this dust. Surveys have given us glimpses behind the veil. The heart of Laniakea, the focal point for 100,000 galaxies including our own, appears to be the Norma Cluster, named for the constellation we look through to see it. It's several times larger than a typical cluster and sits about 220 million light-years away. Even at over 100 kilometers per second, it would take over 100 billion years to reach Norma. Norma formed like any cluster from countless mergers and gravitational attraction. It sits at the bottom of a deep gravitational well, the main point of attraction for this entire region. It will only grow larger as it collects more material. But recent studies using the same reconstruction technique show our motion toward the Great Attractor, the Norma Cluster, isn't the whole story. For one, Norma seems a bit too small. Even with its dark matter, its gravity isn't quite strong enough to explain our speed toward it. In other words, the Great Attractor isn't as great as we thought. There seems to be an even larger source of attraction beyond Norma, because Norma itself is moving. An entity even larger, over 650 million light-years away. This structure was first faintly seen by Harlow Shapley in 1930. We now know it as another supercluster, our neighbor to Laniakea, and it appears even larger than our own. The immense mass of the Shapley Supercluster influences galaxies, groups, and clusters for hundreds of millions of light-years around it. Given enough time, Laniakea would collapse into a single compact object, a much larger version of the Norma Cluster, and that object would eventually be drawn toward the center of the Shapley Supercluster. There are even hints of motion on larger scales. In 2008, NASA astronomer Alexander Kashlinsky observed a subtle signal in the cosmic microwave background called the kinematic Sunyaev-Zeldovich effect. This dark flow caught up a significant portion of clusters. The puzzle is that density variations in the universe aren't large enough to explain such a coherent, large-scale motion. In 2013, scientists with the ESA's Planck satellite found no evidence for this dark flow, but debate continues. Whether dark flow is real or not, echoes from the distant past still shape the cosmos. When the universe was only a few 100,000 years old, it was a hot, dense plasma. Sound waves called baryonic acoustic oscillations rippled through this plasma. When the universe cooled and became a neutral gas, these oscillations froze in place as tiny density fluctuations. Over hundreds of millions of years, these slightly denser regions attracted more matter and more galaxies. Today, cosmologists map these oscillations in large galaxy surveys to test models of cosmic history. In 2023, Brent Tully, Cullen Howlett, and Daniel Palmer discovered that many nearby clusters, walls, and structures are arranged in a shell over 400 million light-years in radius, including structures like the Sloan Great Wall and the Hercules Complex, centered on the Boötes supercluster. They believe this shell is a single baryonic acoustic oscillation, a remnant of the universe's early plasma echoes. Finally, ancient echoes aren't the only forces at play. We are pulled by gravity. From Andromeda, the Virgo Cluster, the Great Attractor, the Shapley Supercluster, and Haulilana. But there are also pushes, sources of repulsion. Adding up all known mass in the universe still doesn't fully account for the Milky Way's motion. There appears to be something on the opposite side of the sky from the Shapley Supercluster that we haven't fully mapped. A great void, an expanse of near-nothingness. Called the dipole-repeller void, we don't yet know its exact shape or size. We just know it participates in the large-scale motions of the universe. These great voids don't just lack matter. They actively push galaxies away from their edges because they are filled with dark energy. Eventually, the repulsion from voids will unwind the cosmic web and prevent us from ever reaching the Great Attractor. There was perhaps one time Einstein didn't trust his own math. Early in his career, his insights were grounded in deep physical understanding. In a single year, he crafted special relativity, contributed to quantum mechanics, and proved atoms exist. But in 1917, after developing general relativity, he applied it to describe the entire universe. His equations predicted a dynamic universe, either collapsing or expanding. This contradicted the prevailing belief in a static, unchanging cosmos. For whatever reason, Einstein didn't want to disrupt the established view. He found a way out by adding a cosmological constant to his equations, a number that, on large scales, could stabilize the universe and counteract its natural tendency to move. Just a few years later, Edwin Hubble discovered the universe was indeed expanding. Yet the constant never fully disappeared. Soviet astrophysicist Yakov Zeldovich later equated it to the vacuum energy of space-time. Then, in 1998, astronomers found the universe's expansion was accelerating. The likely cause: the vacuum energy of space-time. Cosmologists quickly revisited Einstein's blunder, realizing this little term in the equations might be tearing the universe apart. 5 billion years ago, the universe's expansion diluted matter enough for a new force to emerge triumphant. This force was always there, woven into space-time itself, but it was weak, letting radiation and matter dominate cosmic evolution until its time came. We don't understand what dark energy is, only what it does. It causes the universe's expansion to accelerate. Its influence is only growing. As the universe expands, matter spreads out, but the expansion creates more dark energy. It seems linked to the vacuum energy of space-time. Imagine a completely empty box. Quantum mechanics tells us the vacuum is not empty, but a seething sea of virtual particles popping in and out of existence, giving the vacuum its own energy. Dark energy appears to be a manifestation of this vacuum energy. More empty space means more dark energy. 5 billion years ago, the density of matter dropped below the density of dark energy for the first time. Since then, dark energy has dominated. Today, it makes up about 70% of the universe's content. In the future, it will be 90%, then 99%, building on itself as the universe expands and the expansion accelerates. Dark energy will not let the universe rest. It has already begun deconstructing the cosmic web within the voids. Voids are, by definition, almost empty of matter, just occasional wisps of gas or small dwarf galaxies. They are almost pure vacuum, which means they are filled with dark energy and driven to expand by its repulsive force. Voids are where accelerated expansion happens. As time passes, voids will grow and merge, pushing galaxies at their edges apart faster than gravity can hold them together. The only objects that will survive are those already tightly bound by gravity. Our local group will survive, though its galaxies will merge. Clusters like Virgo will also survive as safe harbors for their thousands of galaxies, but superclusters will not make it. Laniakea, Shapley, and millions of others that form the cosmic web's backbone will not hold together. It's too late. They didn't have time to bind themselves tightly before dark energy began its work 5 billion years ago. Finally, we will never complete our journey. The Milky Way will merge with Andromeda, but the local group will never reach the Virgo cluster, let alone the Great Attractor or what lies beyond. Billions of years from now, our motion toward the Great Attractor will slow, stop, and reverse. Over hundreds of billions of years, distant clusters and galaxies will dim and fade, eventually disappearing over our cosmological horizon, carried away by dark energy's accelerated expansion. Trillions of years from now, the mega-galaxy that was once the local group will be utterly isolated, adrift in a sea of nothingness as every other galaxy vanishes. But even then, motion won't cease. Gravitational interactions within this future galaxy will randomly scatter stars. Once a star slips outside the galaxy's gravitational embrace, it too will be caught in the accelerated expansion, flung away as if it never existed. Star by star, the galaxy will diminish. The same fate awaits every large object. Hundreds of trillions of years from now, every dead star, every frozen planet will be completely isolated, separated by vast gulfs of space expanding faster than light. If you found this journey through the cosmos fascinating, please show your support by subscribing to the channel, liking this video, and sharing it with someone who might enjoy it. Your engagement helps us continue exploring the universe's greatest mysteries. Thank you for watching For Company, the universe. What's left of it will finally come to rest. If you found this journey through the cosmos fascinating, please show your support by subscribing to the channel, liking this video, and sharing it with someone who might enjoy it. Your engagement helps us continue exploring the universe's greatest mysteries. Thank you for watching.